Welcome everybody on Zoom, welcome everybody in the lecture hall, welcome everybody from the future. Today we are going to continue to explore MapReduce. I gave you an appetizer about this last week, if you remember, with counting the Pokemons. And that's actually pretty much how it works, right? Now I'm going to go through the formalism of that on a higher level to see how we can actually do the same with data. And the main idea is that we have, in the first few weeks of the semester, we looked at the storage layer, how we manage to store a large amount of data. We looked at the syntax, at the models, at the validation of that data. Now, it doesn't matter if it's on S3, if it's on HDFS, if it's on HBase, if it's on Azure Blob Storage. It doesn't matter if it's text, if it's XML, if it's JSON, if it's Parquet. It doesn't matter at all. Whatever that is that we have now as data, wherever it is stored, the paradigm to query it is going to be more or less the same. All the technologies that we will cover this week and in the next weeks, they work with all of that, all of these storage layers and all of these data models. The idea is actually pretty simple. I told you about the impedance mismatch that we have. We create so much data now, we can store so much data, but we cannot read it fast enough. And the trick, in order to solve the problem, is to parallelize. So we shard, we partition, we split, we chunk. There's plenty of verbs to express this, the data. The idea is it's pretty close to this Banksy work of art. Data is in the shards. And that means that if we look at the structure of queries, what is it on an abstract level? We have some input data, and we want to produce some outputs data. And in the middle, there's the query that we want to execute. Could be a lot of different queries, could be some aggregation, could be some selection of specific records. But no matter what the query is, the main idea behind MapReduce is that there are cases in which you can actually execute the query in parallel because there is no communication between the shards. Right? If you apply, for example, on each one of the 1 billion records, some transformation, then you can do it in parallel, right? And so there are cases in which that actually works. So you can do on every machine, on the data that there is on the machine, you execute the query. In the real world, this is more how this could actually look like, a real spaghetti, where in order to compute something in the outputs, so for example, imagine that I'm looking, so this is probably a billion records in here. I'm looking at one record here. How is it computed? Imagine that it's a sum or an average or a count. Then you see it needs all of the data to compute that one record here. So you see that doesn't work. You cannot do it in parallel. This is a huge spaghetti, and the data just has to fly and flow around in the cluster. So that would be a nightmare, actually. If you have to do this, the complexity of that is actually insane. But in the real world, things are neither quite like this, that would be too easy. Things are neither quite like that would be too difficult. It's kind of in the middle. And that means that at some places in your query, you have things that can go in parallel, that you can actually optimize by executing in parallel. And there are other cases, other places in the query where you have this spaghetti. We'll call it shuffle very soon. So there is a bit of this and there is a bit of that. And that's the idea behind MapReduce, is that it provides a very simple structure for the query with plenty of things in parallel, then the spaghetti, we shuffle around, and then again, plenty of things in parallel. So the first phase that goes in parallel is called the map phase. And the second phase that goes in parallel after the spaghetti is called the reduce phase. That is the high-level view of MapReduce. It is incredibly simple, and yet you wouldn't imagine the quantity of actual problems for databases that can actually be solved like this, with a structure like this. It's absolutely amazing. I'm not saying everything can be solved like this in one go, right? Just running that once. Sometimes you have to do this 10 times or 100 times, right? Sequentially. But the structure here is both simple and generic. And that is why it was a great invention, this MapReduce. All right, so if you have to take a snapshot in your brain of MapReduce, this is it. Take this one, and remember, this is the structure of MapReduce. And now I'm going to just go into the details of that. The data, so I told there's the input and the output. There is also a third place where the data that we are going to look at is relevant. That's the intermediate data. So the intermediate data is neither the input nor the output. It's the data that gets shuffled around like a spaghetti in the middle, right? In the case of the Pokemons, that was the pairs with the counts, but that haven't been summed yet, right? That was the intermediate data. All right. Now, diving more into the details, let's look closer at that data. There is an assumption that MapReduce is doing. MapReduce is assuming that the data in the input and that you want to produce in the output is just a gigantic collection of key-value pairs. So of course, if you have a hammer, you see everything in the world as a nail, right? And that's pretty much what happens with MapReduce. So when you use MapReduce, you see everything as a collection of key-value pairs. But in fact, it's quite accurate because even if something is not quite a collection of key-value pairs, you can still make it fit. We will also look a little bit like that. So everything is a key-value pair. And if you look at the types of the keys and the values, that can be pretty much anything, right? The keys could be integers, or the keys could be dates, or the keys could be strings, names, for example. For example, if you have a collection with, I don't know, some database with the population of Switzerland, you could have the social security number as the key, and the value with the actual records. All right, and so we have some key type and some value type for the inputs. We might have a different key type and value type for the intermediate data, and yet another key type and value type for the output. The key values, we've seen them all over the place in this lecture. Remember, we've seen them when we looked at object storage. We've seen them when we looked at HDFS. We've seen them again when we looked at HBase and so on. It's just the key value model, right? So this is something that by now you should be familiar with. All right, in practice though, the intermediate data uses the same types of keys and values as the outputs very often. I would say in 80%, if not 90% of the cases, it's just the same as the outputs. And what reduce actually does is just that it aggregates the intermediate data with the same key, with a sum or an average or whatever. That's a very common case. Okay, so now I'm going to walk through this more detailed, but not with Pokemons this time, because now we can abstract a little bit away. So I'm going to do it with more generic diagrams. So remember that just like the hammer and the nail, we see everything in the world as a collection of key-value pairs. So whatever arrives from the left is a collection of key-value pairs. It doesn't matter if it's a huge collection of text, if it was JSON lines with one JSON object per line, if it was XML stored in HBase, it doesn't matter at all, or if it was a Parquet file. We view that as a collection of billions of key values. Right. Okay, how these key values are obtained from text or JSON and so on, I'll come back to this later. Now we just assume these are key values. So the first thing we do, that's a logical walkthrough, right? That's on the logical level, it's the math. We split this gigantic collection of key value pairs into partitions, blocks, chunks, splits, whatever you call it, right? In MapReduce, I think we use the word split very commonly, so we'll call them splits, right? So I have now, let's say, 1,000 splits of each 1 million key values, right? And the next thing that we do is that we apply some mathematical function called the map function to each input key value key, each one of these billion key value keys, right? We apply it and we obtain 0, 1, or more intermediate key values like this. It can be 0, it can be 1, it can be more, very generic. And now this I just showed you in a single key value. We do the same with all of the billion key values, right? But of course, we do it on each split, right? So maybe the first is on one machine, the second is on another machine, and so on, right? So we apply the mapping function to each key value of every split, and then we put together for every split all of the intermediate key values that we got. All right, who is following? Okay. So then what we do is that now that we have obtained for every split and for every key value in every split, all of the intermediate key values, we logically put them all together again as a gigantic collection of key value pairs, and that collection of key value pairs is my intermediate data, right? That's the one that gets shuffled around. So now in order to shuffle it around, we need to do something. We are going to sort all of these key values. So we sort in them by key. So then that means that I have all the key one, key one, key one, key one, and then I have key two, key two, key two, and then key three, key three, key three, and so on. I just sort logically by the key. Now I have a sorted collection of key value pairs, right? And just a remark in parentheses, when we looked at the key values in HBase, they were always sorted, right? Remember, when we write the H files, they were always sorted. In the case of MapReduce, the input data or the output data doesn't need to be sorted. There is no requirement of that, right? That's not a requirement. But when we do the shuffling, this is when we need to actually sort them explicitly. In fact, the input data could even have duplicate keys and nobody would complain. MapReduce doesn't even matter if the keys have duplicates or not. Okay, now you see there's even duplicates in the intermediate data, and that's fine because now we're going to put them together, those that have the same key. All right. So now I partition again the data to make sure that all the key values that have the same key, they are together in the same split. And now comes the second phase. I apply the reduce function to every group of key value with a specific key. In that case, it's key one. And again, I emphasize it is important that there is only one call of the reduce function for one group with all the intermediate key values with the key one. It has to be all of them, cannot be a partial evaluation or something. So you need from everywhere, no matter where they come from, all of the key values that have the key one together, you call the reduce function and get some output key value. It can be 0, it can be 1, it can be more. In that case, it's just one output. And again, as I told you, the type of the intermediate data very often is the same type as the output. And what happens is that this reduce function that you see here, very often is going to be a sum. For example, value A plus value B plus value C, and that gives you the output value. Could be an average, could be a count, could be a mean, could be a max, and so on, right? So very often the reduce function is just the call of an aggregation function, right? Okay. So in that case, we get only one, but again, in general, it can be more than one, it can be less than one. That's generic enough to let you do whatever you want. Now, who decides what the map function is and who decides what the reduce function is? You, the user. You give the map function and the reduce function to the system, and they will use the function that you provided to do these calculations. Okay. All right. So now that was just for one group of key values that had the same key. Now we do the same for every single group we call the reduce function, and we get plenty of output key values. Here again, that's the specific case where there's exactly one output key value for every group, but that's only because it's 80% of the cases it's like that, but it doesn't need to be, just to make sure. Okay, now I'm zooming out. So what happens? We map, we sort and partition on the logical level. That's how we do the shuffling, right? We make sure that we sort and group the intermediate key value pairs. Then we apply the reduce function on every group of key values, and it has to be all the key values that have a given key that needs to be together, fed into the reduce function. Who followed? Okay, that's the same thing as the Pokemons, but just more generic, right? Okay, so this is it. That's the power on the logical level of MapReduce, and it's incredible all you can do with that. In fact, you can implement the whole of SQL like that. You can implement select, select from where, group by, having, you can implement all of that with MapReduce. The group by, the sort by, the where, the selection, the projection, everything. It's really amazing. I'm going to show you a little bit how this is done. So the fact that you can implement SQL on top of this is amazing, because in fact, that means that you can, at least in theory, but we'll see it actually in practice, execute SQL on top of MapReduce, on top of a cluster of machines. That's magical. right? Because before we could only execute SQL on one machine with PostgreSQL, right? So now we are getting closer to executing SQL on a data center of machines. Okay, so now that I explained to you the logical level, I'm going to move over to the physical architecture, how this is actually implementing. It's very interesting to see. And we'll see that some of the parts are similar to what we saw in HBase. So a lot of what you learned earlier will actually be useful. Okay, so that's something I already said. We have all of these storage layers, the local file system, HDFS, S3, blob storage, and so on. It doesn't really matter. It's all working. You can use Hadoop MapReduce on top of that. Just a word on Hadoop. Hadoop MapReduce is the open source implementation. The original one, that's proprietary. So the MapReduce, as it was done at Google, is proprietary. Hadoop MapReduce is the open source version of that, right? It's very similar, except that this one anybody can use. Okay. So just to give you an idea, I already gave you orders of magnitude. MapReduce can handle terabytes and even petabytes of data without any problem. It can run on thousands of nodes, thousands of machines in a data center in parallel. And in fact, people did it. People actually executed that on that quantity of data. There are even contests, for example, who can sort a petabyte of data in as little time as possible. And every couple of years, you see that the record is broken with yet another technology that manages to sort in this way. All right. So now, physical architecture. So I have again these diagrams. That was HDFS, right? We have the name node, that's the coordinator node, and then we have the data nodes running on the worker nodes, right? We saw that the same thing happens with HBase, where we had the HMaster, that is a process running on the same machine as the name node, and we had the region servers that are processes running on the same machines as the data nodes, right? These are the same machines here, but just looking at different processes running on them. A process is like on your laptop, maybe you have at the same time your browser and Excel and plenty of software running. That's the same here. This is like Excel and this is like your browser and so on. Just processes running on the same machine. All right. Well, surprise, surprise. It's the same for MapReduce, at least the first version of MapReduce. So I just need to give you the names. The central process that is running on the coordinator node is called the job tracker. And the processes that are running on the worker nodes are called the task trackers. So now we have 3 processes running on each machine, right? Okay, and what happens is that, again, they are on the same machine, so it's co-located. This is the trick, and this is what makes MapReduce super powerful, is that when you do the mapping phase, the task tracker that is in charge of executing the map function is on the same machine as the data nodes. That means the same machines as the HDFS blocks. It means that the task tracker can directly read from the local drive the blocks because they are on the same machine. So this is very powerful. This is called bring the query to the data. Bring the query to the data. It's the idea that instead of trying to move over the data to some place where you run the calculations, you move over the calculations directly to the data. On all the machines, you make the calculations. So this is why we have a task tracker on every machine. So roughly speaking, every split in MapReduce corresponds to 1 HDFS block. So every split is around 128 megabytes of data, roughly. I'll come back to why roughly. But every HDFS block is roughly 1 MapReduce split. And again, they are on the same machine. They are locally stored on the drive. There is 1 replica and of course 2 other replicas somewhere else, but there's 1 replica in the machine. And now we have the task tracker that instantiates so-called threads. You might have heard of a thread. So a thread is the same process might be running in multiple threads. Who heard of a thread on a computer? Okay, so a thread is kind of a logical way of making sure that even if you have a single CPU core, you can still share the resources between different programs or different code. So this is called a thread. All right. So it means that the task tracker that is running on every node here has some mapping thread and some reduce thread, and they are just all triggers executed. And then what happens is that they start processing the data. It might happen when I said it's read locally from the local drive because we bring the query to the data. It might sometimes happen that this is not possible. So maybe you will occasionally have a task tracker that is actually going to process data from a different node. Then you have to ship it over the network, right? All right. So if you now start processing the actual data, you will have all the, these are called map slots. I'll come back to the terminology, but these are the map slots that are in charge of executing the map function. And these map slots are going to take the blocks locally that are sitting on the machine, and they are going to call the map function on this data and then produce the intermediate data. So you see, this is all in parallel on every machine, right? And at that point, if you generate your intermediate key value pairs, there is a risk that you're going to fill the entire memory on the machine, right? Because this is on every machine. But at some point, if you produce so many key value pairs that the memory becomes full, then you need to split it to disk. Does it ring a bell? We've already seen that. We've already seen that with HBase when the memory is full with the cells. And what did we do? What was it called in HBase when the memory was full? What did we do? Yes? Flush, exactly, that's a flush. So here it's called a spill, but this is the same thing. It's a flush, basically. So we flush everything to disk. This is what happens if the memory is full. And then maybe the memory is going to become full again, then we flush again. And what happens if now we have flushed too many times? We start. What is the other one? We have multiple chunks of intermediate data, and we want to avoid that there's too many of them, so we compact. Yes, I heard compacts. So indeed, so you see everything you've learned with HBase that applies here. So this flushing and compacting, we can also use that at the end of the map phase if the memory becomes full. So even the logarithmic version with the LSM trees, that all works. All right, so this is from HBase. The same can be used here in order to handle the data if it doesn't fit in memory. Okay, so next, we have completed everything. Maybe we spilled to disk and flushed and compacted and so on. But now the data, the intermediate data is sitting on all the machines. But in order to be able to execute the reduce phase, we need to shuffle the data around because now we need to make sure that all the key values that have the same key, they are together, right? Because let's assume key one. I'm looking at a key called key one. Where will be the key values associated with key one? Everywhere. They could be in here, they could be here, they could be here, they could be there, everywhere. So you need to bring them all to the same machine in order to be able to do the reduce. But of course, there's probably 1 million keys, so you're going to spread the responsibility for the 1 million keys across the machines, right? It's just like for the Pokemons that every student was responsible for 1 or 2 Pokemons, right? It's the same thing. So every node on the reduce side is responsible for specific keys, and all the key values with these keys are retrieved and shuffled over to that machine, right? So what happens if now I zoom in a little bit on what's happening? If we have some reduce slot that is supposed to execute the reduce function on some specific keys, that reduce slot needs the data. So that reduce slot is going to connect to every one of the machines in the cluster, saying, okay, I need these keys, ship them to me. And then it's going to download for every single machine on the cluster, all the keys, all the key values that correspond to the keys that reduce slot is in charge, right? And then it can execute the reduce function on this. And this happens to be done over HTTP, the protocol. Okay? So then there's the reduce phase that is happening after the shuffling. And then what's going to happen is that the output data often is going to be written down to storage again, to HDFS, to S3, to HBase, to whatever. Let's assume HDFS for a moment. So we write back the output to HDFS. how is it going to happen? What's not going to happen is that we write a single large HDFS file. That wouldn't be practical to do. Instead, what we do is that every one of these slots here, R, where you see R, is going to write separate files to HDFS. For every group of key value pairs, we are going to maybe several groups together, because if we do it for every key, that would be too many files, but we are going to write plenty of files to HDFS. This is the reason why, if you look at the output of MapReduce on HDFS, you're going to see increasing integers. Shard1, Shard2, Shard3, Shard4, Shard5, maybe 1,000 of them. Every one of these shards is a partial data set, a partial output data set. Okay, who is following? Okay, and this is why. So this you see here, part 1, part 2, part 3, and so on. So this is what's typically going to happen. It might still be several blocks for every one of these parts, but what's important to understand is that on the logical level, every one of these parts is an HDFS file, right? It's an HDFS file. And typically, they will all be put in the same directory. So as a user of MapReduce, you say, this is my input. You say, this is my map function. This is my reduce function. And this is the directory to which I would like the output to be written. And then in that directory, you will see 1,000 files. And these are the output key values, output separately in different files, right? So you see now why it was important that a system like HDFS or S3 can have multiple people writing to it in parallel, because now we're going to have all of the nodes in the data center that are at the same time writing files to HDFS. Okay. Any questions so far? Okay. I'm going to come back. That's already, I think, the third time that I explain MapReduce, the whole process of MapReduce with a different angle, and I will have a fourth and a fifth time. So I will keep repeating the process, and every time it will become clearer and clearer, right? I did it once with the Pokemons, once with the logical view, once with the physical view, and I'll do it again in an even more detailed fashion, right? And at the end, things should add up for you. Okay. So there are no questions? And on Zoom, any questions? Okay. So I'm going to continue, but do not hesitate to interrupt me. We have the time, and we'll make sure that you understand everything. So now, I told you, if you have a hammer, everything in the world looks like a nail. So MapReduce assumes that everything is a collection of key values. And of course, that's not true. Not everything is a collection of key values. I'm not a collection of key values, right? So if you look at the data, not everything is. So what I need to explain now is how we can manage to actually look at data, text files, JSON lines, XML in HBase, and so on, how we can actually interpret that as key values so that MapReduce can do something with them. So we have ways to plug MapReduce to an input. And there are several ways. It can be plugged to tables, and it can be plugged to files as input. So there are two kinds of tables that you can plug it to. First, there are the good old relational tables. PostgreSQL, MySQL, IBM, Oracle, and so on. These are all relational databases. And so the first thing that you could do is try to run MapReduce on top of a relational database. What is the key value pair? What would be the key value pairs? How do you see on the left this relational table? How can you see it as a collection of key value pairs? What would be the keys and what would be the values? We've seen that a table is a collection of rows, right? Remember, a table is just a gigantic collection of rows. So we could naturally map every row to a key value, right? So if I have a table with a billion rows, then that gives me a billion key values, right? One key value for every row. But what should we put in the key and in the value? Well, you might remember that when you have relational tables, you also have what is called the primary key. Who remembers the primary key, right? So when you have people, that would be the social security number. If you have the I don't know, the Gemeinde of Switzerland, that would be the zip code, and so on and so on, right? So this is the primary key. So it's quite natural to say that whatever columns, because there can be several columns in a primary key, whatever columns are the primary key, this is going to be the key for MapReduce. So I'm using the primary key of the table as the key for MapReduce. And what is the value? Well, it's the rest of the row, or even the entire row, if you don't mind storing the primary key twice, right? So the key is the primary key, and the value is my entire row or the rest of the row. For whom is that clear? Right? It's a very natural thing to do, to map a relational table to key values in this way. So you see, a relational table can be seen as a collection of key values. And that's great because then MapReduce can actually process key values. And back, right? You could also produce as the output of MapReduce key values that are in fact relational table rows, and then write it back. Instead of HDFS, you write it back to a relational database, right? But of course, the size of a relational database might not be very large. So if you want even more, you can use HBase that has a similar model. And here, what is the key in HBase? What would be a natural way of interpreting an HBase table as key values? What is the key? It's in there on the slide. The row ID, yes, exactly. The row ID would be the key. And then the values, that would be everything else, all of the other values. So here I would have 1, 2, 3, 4, 5, 6 key values, and the keys would be the row ID and the values would be the rest. Okay, so it's a very natural thing to do, and we can interpret a relational table or an HBase table as a collection of key values. Okay, and from then on, we can just apply the map function and so on, as we saw. Okay, so this is for the tables. Now, if you look at files, as I showed you, there's plenty of different kinds of files you could have in HDFS or in S3. You could have text, you could have JSON lines, you could have XML, you could have plenty of different kinds of text. Sequence file, I'm not going to focus too much on that. It's just some binary formats that was invented with MapReduce, but you can actually just imagine it's Parquet. That would be, all right. So, but what I need to explain is now, how on earth are we going to interpret a text file as a collection of key values? How are we going to do that? A text is not a collection of key values, right? However, if you look in a book, it's text, right? It's just a sequence of words. But if you look in a book, you will also see that there's new lines, right? You have lines in text with this carriage return character that we use in computers. So we have lines. So what we could say in a very natural way is that every line of text is going to give me a key value, right? So if I have a billion of lines, then I'm going to get a billion of key values. So I just separate my text based on these new line and carriage return characters in such a way that I get a key value per line. But now, what is the key and what is the value? Well, the value is the line of text. And I'm going to take as the key an offset. I'm just going to put a number there that is just the number of characters since the start of the document, right? So the first one is 0 because that's where it starts, so lorem ipsum dolor. Then citamet, that's 18 because there's been 18 characters before the second line, then 27, 38, and so on. So this is the key. It's kind of arbitrary, but that works. And it's likely you will ignore it when you map. Actually, you will only look at the text, but who cares? We just needed it to be a key value so that it fits in MapReduce, right? And then the map function, you can put anything in there. So in your map function, you can focus on the text. Okay. There is another way of doing that. If you have a data set with a special character that separates something on the left and something on the right on every line, then you can use that character to separate the key and the value. Here, I just arbitrarily put this big black circle. Disk circle normally is only around it, and disk would be the full thing, so a black disk. But it's only for pedagogical purposes. In reality, it's often going to be a semicolon or a comma or a space character and so on. But basically, you can decide, and then you can split every line in two parts, what's on the left and what's on the right. Okay, and that also gives you key values. Okay, so now let's take this as an example. So now I have this text. Maybe it's all of the Sherlock Holmes work or Shakespeare or whatever. And I want to count how many occurrences of every word there is. It's just like the Pokemons, but instead of counting Pokemons, I'm counting words. How do I do this? So I have my text. I can see it as key values in like this. So tell me, what map function and what reduce function should I be using if I want to count how many times every word is appearing in the text? What map function and what reduce function? Remember that a map function must output key value pairs, and a reduce function also. Give you a few minutes. Anybody in the lecture hall? Yes, we can throw the microphone.
Sorry. Maybe you can keep the same key and output as a value the number of times the word you're looking for appears in a specific key.
Like this?
Oh, yeah. I thought you wanted only a single type of word, but yeah, if you're looking for a lexicon, yeah, I guess.
So you mean that if the same word appears multiple times on a line, you count that number?
Yeah, can't you do it at this step? Or is it too early to count, to sum up?
In fact, both work. Both work. You can either do it by outputting every time with a 1, saying it's a count of 1, or you can also directly count how many times it is within a line and directly, for example, if lorem was twice on the line, you could directly say lorem 2. Right? That's what you meant, right?
Yeah.
Yeah. Mm-hmm. So this is the idea. I'll come back to it because directly outputting the number of times it appears in the row instead of just a 1, it's an optimization that is already an advanced usage of MapReduce. It's called combine, and I'll come back to it. Yeah, but basically it doesn't matter whichever way you pick, if you output every word with a 1 or not, or if you already combine. Okay, so great. So this is my map function. What about the reduce function? Anybody else? What should be my reduce function? Yes, the sum function. Exactly, I see on Zoom. Exactly. We just sum over. And you see that this works no matter which strategy you picked. If you output a key value for every word and even a 1 every time, and you sum, that's going to work. If you directly output if it happens multiple times on the same line, and you directly output the count, the sum will work too. Right? Okay, so that's my reduce function. And then in the end, I will get a collection of key values, one key value for every distinct word in the text. And I will get for every word the value as the count in the entire collection. Who understands that this map function and this reduce function do this, counts the words in a document? Okay, and on Zoom, do we have raised hands on Zoom? Who understands that these two functions are going to count the occurrences of every word in a collection? Raise hands on Zoom. Okay, see raised hands. Okay. I was about to say raised hands from the future, but that's not going to work. All right. So map, reduce. Now let's do something else. Let's try to implement a relational database selection. Remember what a selection is in a relational database. A selection is when you have rows in a table and you select some of them. You have some criterion and you say, I want this row, this row, this row. For example, all the people who are older than 65. That would be a selection criterion. So how do we do it in MapReduce? What would be my map function and what would be my reduce function? Anyone? How can I implement a selection? So here I just put texts, could also be database rows, right? Anybody? It's like a Lego game, right? I have a generic system. All it needs is a map function and a reduce function. And you can put whatever you want as the map function and the reduce function, even simple functions that would work. So what should I use as the map function and reduce function in order to filter. For example, I want all of the lines that contain the word data. How could I do that? Anybody on Zoom has an idea what map function and what reduce function I could use? Nobody? I will tell you, of course, but I wanted to give you a chance. All right, then I'm going to tell you. I think it's what happens. It's very early. It's 8 a.m., almost 9 a.m. now, but it's, somebody, yes?
One,
yeah?
Boolean operation that return truth.
Yep, exactly. That's what we need. So that's the predicate. So we need to implement some Boolean function that returns true if we accept the line or false if we don't accept the line. And indeed, once we have these functions, we implement that function. And then what we do is that the map function is going to output the line, so the key value unchanged, if this Boolean function returns true, that was suggested on Zoom. And if that Boolean function called on the line returns false, then I don't output anything, right? So for my first key value, let's say this Boolean function returns true, I'm outputting the key value, the same one, it's really the identity. I take the key value and literally spit it back out in exactly the same. That's because my Boolean function returned true. If my Boolean function returns false, I output nothing, 0 key values. I told you it's 0, 1 or more, right? So here it's 0, nothing. And here it returns false, 0, nothing. And here it returns true, so I output a copy of the key value. So my intermediate data, in that case, will just be a subset of the original data. It's just a subset. I just kept the lines that contain the words that I'm looking for or that correspond to the predicate. If instead of rows, these were database rows, that would just be outputting back the row for which the predicate is true, right? So that's very good thinking on Zoom, right? What would be my reduce function? Because again, as the output, I want the collection with all of the lines that fulfill the predicate. So what is my reduce function? On Zoom, maybe you can tell me the reduce function. Nobody? It's actually super simple. Oh yes, yes. A few people. Identity, exactly, that's it. The reduce function is absolutely trivial. It's just the identity. You just exactly output what you have in the intermediate data, you copy it over to the output data. It's surprisingly easy, right? But it's possible because it's generic enough that you can put anything. And indeed, there are many cases in which your reduce function will just be the identity, or the map function will be the identity. That can happen too, right? Okay, so you see how generic this is. Okay. Now, how would I do a projection? So imagine that now I have JSON data, JSON lines. So I have a huge file with 1 billion lines, and every line has a JSON object. Well, first, MapReduce doesn't know JSON. It only knows key values. Everything is a key value. So MapReduce doesn't know JSON. So the handling of JSON, you would have to do yourself. If you are in Python or Java or whatever, you would have to implement yourself. But in Python, that's good because there's a library to parse JSON. So it would be super easy to take the text and parse it as JSON and then use Python. So imagine that now I want to project it to just ID and country. I want to drop A, basically the key A. So I just want to project to value and country. So in that case, I can just do it in the map function because projection is something that you do on every object, right? So my map function can just do that, right? So I take every single key value, which is every JSON object, and I output the same thing, but project it to ID and country. We have a question.
So the map function and the reduce function are used in query analysis of data instead of optimizing the storage of data?
Yes, exactly. It's one level above. Yeah, you have the storage layer, and on top of the storage layer, you have all of that is happening on a higher level on the system, right? All right. And the reduce function then is just the identity. Again, what happened here, the actual of parsing of JSON and then taking ID and country and then serializing back to a string, that's something you have to do as a user. MapReduce will not do it for you, but you implement it as part of the function. Okay. All right, and then the reduce function is the identity. Okay, now you've deserved the break, and I'll come back after the break to this optimization. This is actually coming back to what you said earlier about the two ways of outputting the intermediate data. All right, so thank you very much, and I'll see you in 15 minutes. Thank you.